In this video, we'll briefly review Lewis acids and bases. When we think about a Lewis acid base and Lewis acid base theory, it really focuses on the transfer of an electron pair. So it focuses on an electron pair forming a bond or the bond turning into an electron pair. It does not require hydrogen atoms to be classified as an acid. So we can have an acid without having any hydrogens around. This is our broadest definition of an acid or a base, because now we're looking at the electron pair and what the electron pair itself is doing. So looking at our examples here, we have aluminum trichloride and ammonia. They react together to form a complex. So what happens is the lone pair on the nitrogen forms a bond to the aluminum. And when it forms that bond, we get a new species. The lone pair is going through a reaction. So we can think the nitrogen is donating a lone pair to the aluminum, or the nitrogen is donating those electrons. And then the aluminum is accepting that pair of electrons from the nitrogen. And we'll see this idea of donating and accepting electron pairs a lot more later on. For now, we can think our Lewis base is the electron donor. So it's the species that's electron rich. We also call this a nucleophile. So our Lewis bases are nucleophiles. And they donate the electron. They're the ones that essentially are doing the attacking. They're the ones that have the electrons that create the bond. Lewis acids, on the other hand, are electron acceptors. So they'll accept the lone pair from the base. They usually are electron deficient, and we tend to call them electrophiles because they love electrons. They want electrons. And our Lewis bases are nucleophiles. You can think they love the nucleus. The Lewis acid, it's an electrophile. It loves electrons. Now make sure you keep these two definitions in your mind for the future, because we're going to start using the terms nucleophile and electrophile a lot. So one way we can keep track of electron movement so that way we can determine which one's a Lewis acid or Lewis base, or which one's the electrophile, which one's the nucleophile, we use curved arrows. So as you can see from all the drawings so far, I tend to do arrows when I show electrons moving. This allows us to keep track of everything. And so if we have water as our Lewis base, I'll have the lone pair there, and then I'll show it attacking the carbon of carbon dioxide. Well, we know carbon can only have 8 bonds ever. So one of the bonds here between the oxygen, and it didn't matter which oxygen I chose, one of them is going to move electrons up to the oxygen. So now you can see this oxygen has 3 lone pairs around it, where over here it only has 2. So that's keeping track of the electron movement where I created the bond here. So you can see I created this bond, and those lone pairs got moved. It went from the bond between the carbon and oxygen to a single bond. And so those lone pairs are going to then go and attack a hydrogen. And so the reason it does the second attack is if we think about the formal charge. We know formal charge, if we calculate the formal charge on all of our atoms, this oxygen has a formal charge +1. This oxygen up here has a formal charge of -1. And so if I go through and do this second attack, or second step, where the lone pair is going to grab the hydrogen here, and electrons from this bond are going to move directly onto the oxygen. So now we have a new set of lone pairs there, and a new bond here. Now, if we check the formal charges on everything, 0, and 0. By going and doing the second step, we reduce the formal charges on all of our atoms, thereby creating a more stable molecule. And so let's practice this idea of identifying the Lewis acid and Lewis base and then showing the movement of electrons. So if I have ethanol, and boron trifluoride, think about which one is the acid, which one is the base. And then try to draw the base attacking the acid and your resulting product. Give you a second, pause the video, see how you do. So when we're looking at this, our oxygen has 2 lone pairs. Our boron only has 6 electrons. It's electron deficient. Our oxygen is electron rich. Since our oxygen is electron rich, that makes it the base. And the boron is the acid. Or another way to think about it, the base is also our nucleophile. And the acid is our electrophile. So that means what will happen is the nucleophile will go and attack the electrophile. So take its lone pairs and form a bond to that boron. Which gives us our new product. The oxygen ends up with a positive formal charge. The boron ends up with a negative formal charge. Let's try one more. Here we have our ethanol. And our tert-butane. Try and figure out which one's the base, which one's the acid. Figure out the products. Go. Okay. So hopefully you got the hint where I drew them still electron rich, still the nucleophile, still the base. Since there's a positive charge, very obviously electron deficient, which means electrophile, this has to be the acid. Hey, I drew them in the same spot for you guys. So that means kind of the same thing happens. The lone pair will come and attack that central carbon. There. So now we have our ether product with the oxygen having a positive formal charge. Not too bad, right? As long as you can identify which one is electron rich, which one's electron deficient, you should be able to figure out which one does the attacking, which one gets attacked, or which one donates the electron pair, which one will receive the electron pair. And I do want you guys to start thinking about it more in terms of nucleophile and electrophile instead of acid base.